You know, when you're standing on a platform and you watch a high-speed train streak past, what do you actually see? You probably notice the sheer physical mass, right? The heavy steel tracks, the overhead electric wires, the aerodynamic carriages. But what you are actually witnessing in that moment is a massive, invisible web of data in motion. Today, in this explainer, we're going to look way beyond the physical infrastructure. We're going to examine the telecommunications network that makes modern rail travel entirely possible. We'll explore how this hidden architecture governs literally everything, from the critical safety of the train itself, all the way to that departure message flashing on your screen.
So think of the telecommunications network as the central nervous system of the railway. It is the absolute, undeniable backbone of the entire operation. It facilitates the continuous, high-speed transfer of both safety-critical data and administrative information. And it comes down to a really simple fact. Without communications, trains just cannot move safely. If this invisible backbone were to somehow sever, the signals would instantly freeze, the power grids would isolate, and the entire physical body of the railway would immediately grind to a halt. It's that important.
All right, here's our roadmap for today's explainer. We'll start with the invisible backbone, then categorize the network, dive into voice systems, check out data bears, look at business and passenger systems, and finally wrap up with the modern convergence.
First up, categorizing the network. Safety versus business. Okay, let's dive into this macroscopic view. The railway network is fundamentally split into two broad camps. On one side, you have the operational systems. These are the vital organs. We're talking safety-critical data, highly secure voice links for train drivers, and incredibly robust data circuits that control the physical tracks and signals. These absolutely must have sky-high availability and reliability. Then, on the other side, we have the business and passenger systems. These handle the user experience, managing real-time departure boards, processing massive amounts of ticketing data, and supporting the remote management of all those railway assets.
Moving on to operational systems, specifically voice communications.
To keep everyone, signalers, drivers, track workers, perfectly synced up, railways rely on dedicated ultra-secure radio networks. For mainline railways, this is typically a system called GSM-R, which operates on dedicated frequency spectrums. Now for metro systems, especially down in those long tunnels, you'll often see TETRA radio networks combined with radiating cables that engineers call leaky feeders. These secure links are absolutely critical for day-to-day instructions, but honestly, more importantly, they enable the railway emergency call, or REC. Imagine a hazard is spotted on the track. A worker or driver can instantly contact all trains in a specific geographic area and instruct them to stop immediately. It is pretty incredible to think that a single radio protocol can instantly halt thousands of tons of moving steel, potentially averting a major disaster.
Now, traditional trackside phones might look like a total relic from the 1980s, but they are actually a highly visible, critical fail-safe. It's how we handle communications when digital systems might glitch out or when specific on-the-ground trackside intervention is required. But hey, the hardware is only half the equation here. The other half is the incredibly strict voice protocol used by the humans on either end of that line. When a signaler gives a manual instruction to a driver to pass a signal at danger because of a fault, that instruction must be explicitly repeated back word for word. Misinterpreting an operational message can result in a catastrophic situation, so the human communication protocol itself acts as this essential safety buffer.
Next up, under operational systems, data bearers. So, these are the high-availability data circuits that do the silent, heavy lifting of railway automation. First, they connect the signaling interlockings. Those are the fail-safe computers that mathematically ensure train routes never, ever conflict. Second, they carry SCADA systems. SCADA stands for Supervisory Control and Data Acquisition. In a railway context, SCADA is primarily used to monitor and control the vast electric traction systems over huge areas. This ensures trains have the power they need and allows for rapid power isolation in an emergency. Honestly, this is what prevents you from being stuck on a dark, powerless train out in the middle of nowhere. Finally, these circuits control level crossings, taking data directly from approaching trains to safely lower barriers for road and pedestrian traffic.
All right, let's shift gears to the user experience, business and passenger systems.
Seriously, think about your last trip to a station. How exactly does that platform screen know your specific train is exactly 2 minutes away? Well, it all starts with a system called the train describer. Because conventional track sensors only know that a train is there, not which train, the train describer assigns a unique alphanumeric head code to every single service. As the train moves across physical track circuits, the describer logic virtually steps this digital identity from one berth to the next. This raw location data then flows via Ethernet or Wi-Fi to central processors, which constantly match it against the master timetable.
Finally, those processors push the updates to the CIS and PIS, the customer and passenger information systems, delivering the real-time audio and visual announcements you rely on straight to the platform. It's like a giant, perfectly choreographed puzzle.
Which brings us to remote asset management, or as I like to call it, seeing the future.
The absolutely crucial point here is the massive shift from reactive repairs to proactive intelligence. By transmitting data constantly, engineers can monitor the physical health of the railway from hundreds of miles away. We're talking about detecting a set of track points that's operating just a fraction of a second too slowly, or maybe an error rate that's suddenly spiking on a data link, or even just a single tiny filament failing inside a signal lamp. By catching these anomalies super early, maintenance crews can fix the equipment during planned downtime. This prevents a catastrophic failure that would otherwise freeze the network and cause massive passenger delays. It's a real game changer.
Finally, let's look at the modern convergence, IP-based infrastructure.
This, right here, brings us to the cutting edge of railway tech. For decades, railways deliberately kept operational networks completely physically separate from passenger networks. It just made sense for security. But today, the massive push is towards software-defined networks using IP or Internet Protocol architecture. So the big question is, can a single IP-based network safely carry both the safety-critical data needed to physically stop a train and the everyday business data used for office emails and station Wi-Fi? Can we do that without exposing the railway to cyber attacks or critical delays?
Well, safe convergence isn't just about plugging everything into the same router. No way. To build a secure, unified architecture, engineers actually split the OSI access layer. The mission-critical side uses heavily ruggedized switches and routers. They duplicate power supplies. Actually, they duplicate almost all the components to eliminate any single point of failure. They connect via multiple nodes to ensure there's always a backup path for the data to flow. And because it's an IP network, strict cybersecurity measures like high-level encryption and heavy-duty firewalls are totally mandatory to protect against malware or unauthorized access.
Which leaves us with a pretty fascinating final thought to ponder. Modern trains are no longer just metal carriages on rails. They are literally high-speed rolling data centers communicating continuously with the infrastructure all around them. We've seen how this invisible backbone manages the whole shebang, from electric traction and train descriptions to emergency voices and predictive maintenance. But as these digital and physical worlds become permanently intertwined, the ultimate challenge for engineers isn't just making the trains run faster. It's ensuring this vast, invisible telecommunications web remains completely unbreakable. Thanks so much for joining me for this explainer. Next time you're on a train, take just a moment to appreciate the silent, invisible flow of data that's guiding your journey.